16.4 The work of running water. Outline the ways in which streams erode, transport, and deposit sediment. Streams are Earth's most important erosional agents. Not only do they have the ability to deepen and widen their channels, but streams also have the capacity to transport enormous quantities of sediment delivered to them by overland flow, mass wasting, and groundwater. Eventually, much of this material is deposited to create a variety of landforms. Stream erosion. A stream's ability to accumulate and transport soil and weathered rock is aided by the work of raindrops, which knock sediment particles loose, see figure 6.24. When the ground is saturated, rainwater cannot infiltrate, so it flows downslope, transporting some of the material it dislodges. On barren slopes the flow of muddy water, sheet flow, often produces small channels, rills, which in time can evolve into larger gullies, see figure 6.25. Once flow is confined within a channel, the erosional power of a stream is related to its slope and discharge. The rate of erosion, however, also depends on the relative resistance of the bank and bed material. In general, channels composed of unconsolidated materials are more easily eroded than channels cut into bedrock. When a channel is sandy, the particles are easily dislodged from the bed and banks, and they are lifted into the moving water. Moreover, banks consisting of sandy material are often undercut, or eroded at their base, dumping even more loose debris into the water to be carried downstream. Banks that consist of coarse gravels or cohesive clay and silt particles tend to be relatively resistant to erosion. Thus, channels with cohesive silty banks are generally narrower than comparable ones with sandy banks. Streams cut channels into bedrock through three main processes: quarrying, abrasion, and corrosion. Quarrying. Quarrying involves the removal of blocks from the bed of a stream channel. This process is aided by fracturing and weathering that loosen the blocks sufficiently so they are movable during times of high flow rates. Quarrying is mainly a result of the impact forces exerted by flowing water. Abrasion. The process by which the bed and banks of a bedrock channel are ceaselessly bombarded by particles carried into the flow is termed abrasion. The individual sediment grains are also abrade by their many impacts with the channel and with one another. Thus, by scraping, rubbing, and bumping, abrasion erodes a bedrock channel and simultaneously smooths and rounds the abrading particles. That is why smooth, rounded cobbles and pebbles are found in streams. Abrasion also results in a reduction in the size of the sediments transported by streams. Features common to some bedrock channels are circular depressions known as potholes, which are created by the abrasive action of particles swirling in fast-moving eddies, figure 16.15. The rotational motion of sand and pebbles acts like a drill that bores the holes. As the particles wear down to nothing, they are replaced by new ones that continue to drill the stream bed. Eventually, smooth depressions several meters across and deep may result. Figure 16.15 Potholes. The rotational motion of swirling pebbles acts like a drill to create potholes. Photo by Storm Studio/Alamy Images. Corrosion. Bedrock channels formed in soluble rock such as limestone are susceptible to corrosion, a process in which rock is gradually dissolved by the flowing water. Corrosion is a type of chemical weathering between the solutions in the water and the mineral matter that makes up the bedrock. Transport of sediment by streams. All streams, regardless of size, transport some weathered rock material, figure 16.16. Streams also sort the solid sediment they transport because finer, lighter material is carried more readily than larger, heavier particles. Streams transport their load of sediment in three ways: 1. In solution, dissolved load; 2. In suspension, suspended load; and 3. By sliding, skipping, or rolling along the bottom, bed load. Smart figure 16.16 Transport of sediment. Streams transport their load of sediment in three ways. The dissolved and suspended loads are carried in the general flow. The bed load includes coarse sand, gravel, and boulders that move by rolling, sliding, and saltation. Animation. Sediment transport by streams. Dissolved load. Most
Stream sediment movement. Rock transported by the flowing water of a stream is known as the stream load. The stream load moves in several different ways. Some compounds, such as salts, may be dissolved in the flowing water. Very fine particles of clay and silt are carried in suspension without touching the stream bed. Larger particles, such as sand, may jump or bounce along the bottom in a process called saltation. The largest particles, such as gravel and cobbles, slide or roll along the bottom in a process known as traction. Material moving in solution is known as the dissolved load of the stream. while sediment moving in suspension constitutes the suspended load. The larger material moving by saltation or traction makes up the bed load of a stream.
Dissolved load. Most of the dissolved load is brought to a stream by groundwater and is dispersed throughout the flow. When water percolates through the ground, it acquires soluble soil compounds. Then it seeps through cracks and pores in bedrock, dissolving additional mineral matter. Eventually much of this mineral-rich water finds its way into streams. The velocity of stream flow has essentially no effect on a stream's ability to carry its dissolved load. Material in the solution goes wherever the stream goes. Precipitation of the dissolved mineral matter occurs when the chemistry of the water changes, when organisms create hard parts, or when the water enters an inland sea, located in an arid climate where the rate of evaporation is high. Suspended load. Most streams carry the largest part of their load in suspension. Indeed, the muddy appearance created by suspended sediment is the most obvious portion of a stream's load, figure 16.17. Usually only very fine sand, silt, and clay particles are carried this way, but during flood stage, larger particles can also be transported in suspension. During flood stage, the total quantity of material carried in suspension also increases dramatically, verifiable by people whose homes have become sites for the deposition of this material. For example, during its flood stage, the Yellow River, Huanghe, of China is reported to carry an amount of sediment equal in weight to the water that carries it. Rivers such as this are appropriately described as too thick to drink but too thin to cultivate. Figure 16.17 Suspended load. An aerial view of the Colorado River in the Grand Canyon. Heavy rains washed sediment into the river. Photo by Michael Collier. The type and amount of material carried in suspension are controlled by two factors, the flow velocity and the settling velocity of each sediment grain. Settling velocity is defined as the speed at which a particle falls through a still fluid. The larger the particle, the more rapidly it settles toward the stream bed, figure 16.18. In addition to size, the shape and specific gravity of particles also influence settling velocity. Flat grains sink through water more slowly than spherical grains, and dense particles fall toward the bottom more rapidly than less dense particles. The slower the settling velocity and higher the flow velocity, the longer a sediment particle will stay in suspension, and the farther it will be carried downstream. Figure 16.18 Settling velocity. The type and amount of material carried in suspension are controlled by two factors, the flow velocity and the settling velocity of each sediment grain. Settling velocity is defined as the speed at which a particle falls through a still fluid. The larger the particle, the more rapidly it settles toward the stream bed, figure 16.18. In addition to size, the shape and specific gravity of particles also influence settling velocity. Flat grains sink through water more slowly than spherical grains, and dense particles fall toward the bottom more rapidly than less dense particles. The slower the settling velocity and higher the flow velocity, the longer a sediment particle will stay in suspension, and the farther it will be carried downstream. Figure 16.18 Settling velocity. The speed at which a particle falls through still water is its settling velocity. Deposition of suspended particles occurs when their settling velocities are greater than the stream's flow velocity. Bed load. Coarse material, including coarse sands, gravels, and even boulders, typically move along the bed of a channel as bed load. The particles that make up the bed load move by rolling, sliding, and saltation. Sediment moving by saltation, salter equals to leap, appears to jump or skip along the stream bed, see figure 16.16. This occurs as particles are propelled upward by collisions or lifted by the current and then carried downstream a short distance until gravity pulls them back to the bed of the stream. Particles that are too large or heavy to move by saltation either roll or slide along the bottom, depending on their shapes. The movement of bed load through a stream network tends to be less rapid and more localized than the movement of suspended load. A study conducted on a glacially fed river in Norway determined that suspended sediments took only a day to exit the drainage basin, while the bed load required several decades to travel the same distance. Depending on the discharge and slope of the channel, coarse gravels may only be moved during times of high flow, while boulders move only during exceptional floods. Once set in motion, large particles are usually carried short distances. Along some stretches of a stream, bed load cannot be carried at all until it is broken into smaller particles.